Hello everyone, my name is Rishikesh Dhume.
And I am Pallav Deshmukh.
And I'm Paras Garat.
We are the students of Electronics and Telecommunication Department at Sardar Patel Institute of Technology. We have created Splitify. Our product uses principles of signals, networks, and system to aid real-world audio processing. So let's begin with the presentation.
So let me introduce you to the basic fundamentals of our projects. So basically in signal systems, we studied that any complex signal can be represented as the sum of its simpler component signals. This is known as the superposition principle, one of the most fundamental concepts in linear systems.
In our project, this principle directly applies to music. The mixed song, represented as x of t, is actually the sum of several independent sources: vocals V of t, drums D of t, bass D of t, and other instruments O of t.
So, what our model Splitify does is the reverse of this process. It takes the combined audio signal x of t and separates it back to its original components. This is this is a perfect real-world demonstration of superposition principle in action. Now let us see why source separation matters. So before we get into the technical details, it is important to understand why source separation actually matters. In any song we hear, multiple sounds like vocals, drums, bass, and instruments are layered together in one complex waveform.
For musicians, producers, and audio engineers, it's often necessary to isolate individual components from a track. For example, separating the vocals for a karaoke version or isolating the drums to remix a song. Doing this manually is extremely time consuming and usually requires expensive studio tools.
This is where deep learning comes in. AI models like Demucs can intelligently unmix songs with impressive accuracy. This enables new possibilities from remixing and music education to audio restoration and professional production, all automated and affordable. The main objective of our project was to apply the concepts we learned in signals and systems to solve a real world problem. In our case, music source separation. We wanted to see how theoretical principles can be implemented through modern signal processing and deep learning.
Our first goal was to apply SNS principles in real-world audio processing. Concepts like superposition, convolution, and Fourier transform directly guided how our system works. The second goal was digital decomposition, breaking a complex audio signal like a song into its fundamental components such as vocals, drums, and bass.
Finally, we aim to visualize the theory in action to actually see how the superposition and filtering behave in real world audio signal. By doing this, we connected the analytical side of SNS with practical, hands-on application through our project Splitify. So now let's move towards the fundamentals of SNS in our project. So our project Splitify isn't just any other software project. It's a real-world demonstration of signals and system principles in action. Every step of our model from input to output reflects an SNF's concept we have studied so far, like signal representation, superposition, convolution, and Fourier analysis. Let's go through each of these core ideas and see how they apply directly to our project.
So the first concept is signal representation. Our input starts as a continuous time analog waveform, but before processing, it's sampled and quantized from a discrete time signal, typically at a rate of 44.1 kHz. Next comes the superposition principle, which is fundamental to understanding audio mixing. In mathematical terms, a mixed signal x of t is just the sum of several components: vocals, drums, bass, and other sounds. What Splitify does is essentially the reverse. It decomposes the total signal back into its individual parts, which is the practical use of superposition. Moving on to convolution and filtering. The neural network layers inside Demucs act like adaptive digital filters. Instead of manually designing FIR or IIR filters, the system learns its own impulse response to detect patterns unique to vocals, drums, and instruments.
The next important concept is the Fourier transform. In signals and systems, the transform helps us understand signals in the frequency domain, and Splitify uses the same principle. The model analyzes how energy is distributed across different frequencies to identify which part belongs to vocals, bass, or drums. Finally, when we analyze system properties, we see that Splitify behaves as a causal system, meaning the output depends only on present and past inputs. It's time invariant, giving consistent results for different inputs, and it's non-linear because of the deep learning layers that introduce non-linearity into processing. So Splitify is a perfect example of how SNS theory, from representation and convolution to frequency analysis and system behavior, can be applied directly to solve real-world problems like music source separation.
Now let us have a look at system architecture of Splitify, or in simple terms, how a system processes a mixed song and converts it into isolated audio tracks. The overall workflow follows the same pattern as what we learn in signal and system, where a signal passes through a system, gets filtered, and produces different outputs.
The process begins with the input, which is the mid song, a discrete time digital signal sampled at 44.1 kHz. This signal is then passed through the Demucs model, which acts like a highly advanced signal processing system. Each layer inside Demucs uses convolutional filters that function just like the digital filters we study in SNS, except these filters are learned automatically through training. As the signal passes through the model, these filters detect and separate patterns specific to different instruments such as rhythmic drum beats, harmonic vocals, and low frequency bass components.
So once processed, the system generates multiple isolated outputs. For example, one track for vocals, another for drums, and the others for bass or background instruments. Each output can be thought of as the system's individual response to specific frequency and temporal features within the input, very similar to how we study impulse responses and system outputs in SNS. So the entire Splitify pipeline from input to filtered outputs mirrors a signal flow system, demonstrating how convolution, filtering, and system response all work together in real-world audio separation. So now let's move towards the technical implementation of our project.
Now that we have seen the architecture, let's look at how we technically implemented Splitify. Our system is built using a combination of FastAPI, ReactJS, and Demucs V4 model, along with CD quality audio sampling at 44.1 kHz. Together, these components allow us to process high quality songs, separate them accurately, and present the results through any easy to use interface.
We use FastAPI for the backend, which is modern Python framework designed for high-performance API development. It handles audio uploads, runs the Demucs model for processing, and returns the separated audio stems back to user. On the front end, we use ReactJS to create a clean and interactive web interface. Users can upload a song, monitor the progress, and then listen to or download the separated tracks directly from the browser. This setup gives us a complete full stack implementation, connecting deep learning with an intuitive user experience.
At the core of Splitify lies the Demucs version 4 model, which stands for Deep Extraction for Music Sources. It's a state of the art. The deep learning architecture specifically designed for music source separation. The model uses convolutional filters and recurrent layers to analyze both the time and frequency structure of the song, ensuring clean and natural separation of sounds. Finally, all the processing is done at 44.1 kHz sampling rate, which is the same standard used in professional audio CDs. This ensures that our outputs maintain high audio fidelity and minimal distortion. In short, the combination of fast API, ReactJS, and Demucs creates a powerful yet efficient system capable of performing complex signal separation in real time. Now let us have a look at the project which we have made. So we have used Demucs for backend, which is a deep learning model which separates the drums, vocals, and other instruments from the music which we have input. Then for the front end we have used React.js, and for styling we have used CSS. Now let us have the actual demonstration of our video. So first of all, let us start the backend. Now that the backend has started, let us start the front end. Okay. So first of all, from here we would have to choose a file which we want to separate. So, for example, let us choose this one. Okay. Now let us start the separation. Now the separation will start in the backend. So here you can see the separation is started. Now let us wait for the separation to come. Now let us have a look at the output which we have got. We have got the four files: vocals, drums, bass, and other.
The first output represents the vocals, capturing the human voice clearly while removing the background noise. Play vocals.
You know the rules, and so do I. I've still commitments.
The second and third outputs isolate the drums and bass, preserving rhythm and low end frequencies without distortion. Play. Finally, the last waveform represents other instruments such as guitars, synths, or background harmonics, all separated neatly from the original mix. Each waveform demonstrates that our model accurately identifies and filters the frequency ranges unique to each sound source.
These results show the real-world application of signal and system concepts. The model essentially acts as the system that performs convolution and frequency domain filtering just like we study in SNS. Only here it's powered by deep learning. The clean separation of these tracks proves that our system efficiently decomposes a complex input signal into fundamental components, achieving what we call digital signal decomposition in practice. So finally, let's take a look at our future expansion roadmap for Splitify. Our goal is to take the project beyond static source separation tool and move towards a real-time, scalable, and intelligent music processing system. This roadmap offers the outline for the next 5 stages of improvement which we have planned.
The first step is real-time processing. We aim to implement buffer-based streaming so that Splitify can perform live separation with very low latency, allowing musicians or DJs to isolate instruments in real time. Second, cloud development. We can we plan to scale the system using GPU accelerator interface through platforms like Google Cloud or Hugging Face. This will make Splitify accessible to the world and mobile, removing the need for heavy local computation. The third step is model comparison. Here, we'll evaluate our Demucs model against other popular models like Splitter, and Open Unmix, and fine tune them specifically for Indian music genres, which often have unique frequency patterns and instrument overlap.
Moving on, the fourth step focuses on visual analytics. We want to integrate spectrograms and Fourier visualizations directly into the interface, so users can actually see how separation happens in the frequency domain, connecting the project back to signal processing theory. Lastly, our long-term vision is intelligent mixing. This involves using AI-driven tools to automatically suggest equalizer settings, adjust grain balance, and even provide professional mixing recommendations for creators. With these expansions, Spotify can evolve from an academic project into a powerful creative and educational platform that bridges deep learning and core SNS principles.
To conclude, our project Splitify stands as a bridge between theoretical concepts of signals and systems and practical engineering applications. Through this work, we demonstrated how principles like superposition, convolution, and Fourier analysis, which we usually study in theory, can be effectively applied using modern AI based models for music source separation.
This project shows how classroom learning in signals and systems can directly translate into real-world signal processing tasks. Every block of our system, from signal input to filtering and output, mirrors the system models we analyzed mathematically in SNS. In short, we didn't just study the equations, we implemented them. We converted those core ideas into a working digital system that can process real audio data.
With Splitify, we have seen how theory can inspire innovation. turning academic concepts into creative and practical tools. It's a small example of how signals and systems is not limited to textbooks but plays a major role in audio engineering, AI, and digital signal design today. So thank you for watching our presentation and learning how Splitify truly bridges theory and practice. Make sure to like and subscribe to our channel also.
Thank
Thank you.
you.
Thank you.